we are presenting a short lecture on Verilog for logic design at RT level. Basically what we are doing is we're giving a flavor of Verilog and how this language can be used for describing components of register transfer level, and we are not getting a lot into what register transfer level design is. We are defining what it is, but we are not getting into a lot of details of methodology at RT level. Plus that the Verilog we are covering is just the very basics and not covering a lot of detailed constructs of the language, and plus that the various ways a hardware component can be described is not going to be done here. Overall, we are just doing a flavor of Verilog, and just to get you started with something, by the end of this, you will be able to do small designs, small maybe adders, subtractors, maybe state machines and all that in Verilog, and perform simulations. So what we do is we talk a little bit about RT level design, then we talk about the basic definitions of Verilog, and then get into component descriptions for RT level design, the components that go in the data path and components that go in the controller. At the very end, we will do a short talk on test benches, testing the sample controller that we built in the previous section. So what is RT level design? RT level design is when you decide that you want to do your hardware using a data path and a controller. So you partition your design into a data path and into a controller. The data path includes the components like ALU and register files, adders, multipliers and all that, and also the interconnection of them. The controller has the part that controls the movement of data in the data path and functionality of the components in the data path, and also interconnection of buses in the data path. This is showing a system with some input and output buses and a data path and a controller. See that we have flags and signals going from the data path to the controller. We have signals coming from the controller in the data path, and actually the controller signals in the data path control the behavior of things happening in the data path. In the data path, you are seeing maybe a register, maybe a register file, maybe a multiplier, maybe an ALU, and so on. An ALU is an arithmetic logic unit, is a logic unit that performs logic in some arithmetic functions. Complex ALUs include things like shifters or barrel shifters, multipliers, adders, and all that, or adding and so on. But simple ALUs just do basic logic and basic arithmetic. In any case, my data path includes these components plus their interconnection through the buses. So we have buses that interconnect these components. Then we have these signals coming in from my controller into the data path, where they control, let's say, whether this component is going to be doing adding or subtracting or ANDing or what. These control signals also control the interconnection of the buses. Maybe a register goes into this bus, or maybe another input from the register file goes into this bus, and these control signals control that as well. And then things happen in the data path, and they report that to the controller. The controller will make decisions based on those events, and will issue proper signals for the next state of the data path. Okay, so my data path is this, includes these components, and main buses for bringing data and taking data out come to the data path only and not to the controller. When we are designing this part, we say, well, what do we need? We need logic functions, we need registers, we need buses, and we show how we can describe these. We may need shift registers, or we may need counters or things. And all of these clocking of these and the enabling, the resetting are controlled by these control signals coming from the controller. If my ad has an overflow, maybe this should be reported to the controller, and the controller makes decisions based on that. If I have a processor that has fetched an instruction, the fetching comes in maybe in a register and called, let's say, instruction register. That instruction register will be providing opcode to the controller, and the controller will based on that opcode, the controller will be issuing other signals for things happening in the data path, or maybe for accessing buses outside or so on. And but all in all, what we will be showing is some of the components that go in the data path. Describing data path in Verilog may look something like this. Has data inputs, outputs, flags, opcodes as outputs, and control signals as input. To declare those, I can either have in the header part, I can say input such and such, output such and such, or maybe I can just make a list of all my inputs and outputs and then declare them down here. The preferred way is not what I'm showing here, but I'm just showing that to indicate that it is possible to do it this way. The preferred way would probably be to include the input, the size, along with the name right up here, okay, as we will see the syntax later. Later on, we will also show the other components that go in the data path as well. But for now, we are just saying what happens in the data path. So these are the declarations in data path. These are the inputs and outputs. Again, some inputs come from outside. Some outputs go to the controller. Some inputs come from the controller. And the major set of inputs coming from the controller to the data path are those control signals. A particular data component, like for example that register we were showing, okay, this one over here, that has some of the control signals dedicated to the functionality of that particular component as input, and then it has its own data buses and data inputs and data outputs, which will be decided by the data path where these buses connect, or how these buses connect to other components within the data path. So this is a typical data path component. What happens here? Well, depends. If it's an ALU, it happens in it is a combinational circuit. If it is a register, it has to be clocked, and it has to have a clock input. As I'm going through all of these examples, I'm also showing you basic constructs of Verilog, if you have not been exposed to this language before. Verilog descriptions begin with module, then followed by a name, followed by a header part. The header part can include the declaration of the inputs and outputs. And then the description ends with end module. Within a module, we have either instantiation of other components, Boolean expressions, or behavioral description of the component we are describing. Let's talk about the controller part. The controller part again is a Verilog module, and it is a part that makes decisions. Decisions it makes causes it to issue some control signals for the outside world and some control signals for the data path. On the other hand, the controller takes inputs from the outside world. This is the outside world. Inputs from the outside world, and it can also get inputs from the data path. Okay, and whether it gets the inputs from the outside or gets from the data path, the decisions in the controller are based on those inputs and based on the existing state. So the controller makes transition from one state to another, and once it goes to one state, it issues these signals here and these signals here, and makes decisions, and then it has many states. How does the controller behave, or how is it described? Well, again, it's described as a module with a name, with some inputs, with some outputs, the outputs being these control signals. And then it has a behavioral description describing the state-by-state transitions and the signals that are being issued. All right, before I go into some particular data path and controller components, let's cover a little bit of Verilog. Okay, a Verilog module begins with the name and ends with end module. Okay, and we will be using this yellow highlighted characters for the keywords of the Verilog language. Okay. How can I describe a component? Whether it is a controller component, it is the complete data path, it is a particular component, I can use primitive components. Just like when you're designing, you can always design something like this, right? Gates. Well, I can describe this in Verilog. How do I describe it without even looking at the next slide? Let's see what happens. Well, this is a primitive gate, so I use OR. This is a primitive gate, I use AND. This is a primitive gate, I use this is OR, this is AND, this is a NOT gate. These are the primitives, and then the interconnection. Well, this OR primitive, let's call it U4 for example, just to give it a name, and this is called instance name. The output of it is W, and the inputs of it are A select and B select. Okay, and this is how I describe this OR, and then as you can see, I can describe the AND and the NOT and all that, put them together, that becomes the Verilog description of this. And here it is. This is, of course, a multiplexer that if S is 0, A goes through. If S is 1, B goes through. Okay, multiplexing A or B on W. This is one version of multiplexer, and I am declaring the inputs. Notice that now I'm putting the input declaration right on top, and I'm also declaring the output. This way I don't need to say after ABSW, I don't need to say input ABS over here. But if I don't include the keyword input up there, I have to bring it down here after the header of the module. Then in here I have signals that are not necessarily the inputs and outputs of the circuit, and in order to be able to use those, I have to declare them, and therefore I declare them as wire. Okay, and then the rest of this description has instantiation of these primitives with the interconnection of their inputs as shown over here. A NOT, and a NOT, two ANDs, and an OR gate. The primitives in Verilog, all the time output comes first and any number of inputs come next. Maybe I don't really want to describe this circuit using the gate instances. Maybe I just want to write a description that shows me the W output. So I can say W is, let's see, A ended with S bar, ORed with B ended with S. Okay, I'm using this. If you look at the Boolean, this is a dot, this is a dot, and this is a plus if you are doing Boolean. So Verilog uses these symbols instead. Okay, so let's describe it instead of using gates. Instead of going into so much detail, let's describe it using a Boolean expression. Okay, again the header becomes the same thing. This is a circuit having 3 inputs here, 1 output there, and then an assign statement shows the output is the Boolean function of the 3 inputs. So these are various ways you can describe things in Verilog. If I have a more complex logic, instead of using Boolean, I can use conditional statement. This actually describes the same exact thing. It says I have a component with A, B, S input, and W output, and it says if S is 1, okay, if S is 1, B is selected, and therefore if S is 1, B goes on the output, and it says if S is 0, A is selected. If S is 0, A is selected, goes on the output. Okay, and this is a condition statement. For complex logic, this is far easier to do than writing a complete details of Boolean expressions. And there's still another way of describing this. Through all of these various ways, I'm showing various constructs of Verilog. This is another multiplexer, and here, let's read this. I say that always, when there is an event on A or B or S, the flow begins in this procedural statement. And then when the flow begins, let's look at S. If S is 1, W becomes B. Otherwise, or else, W becomes A. Okay? So, no matter how you look at it, this one, oh, sorry, I went the wrong direction. No matter how you look at it, this is a description of a multiplexer at the gate level. This is a description of a multiplexer using Boolean expressions. This is a description of a multiplexer, same exact multiplexer, using condition statements. Okay, it gets easier and easier as I go forward. And this becomes a description of the multiplexer with a lot of flexibility, with a lot of if-then cases and case statements and things like that, describing the same multiplexer. And another way of describing a multiplexer is by module instantiation, or let's reword that. Another way of describing a hardware is by instantiating modules within that hardware. Okay, for example, if I happen to have this logic, which I'm calling and or logic, which is this and or, okay, A, B, C, D. This is a logic with some output Y, and I have it in my library, and I like to build a multiplexer out of this. Okay, well, first of all, let's look at the and or circuit. The and or circuit is Y equal I1 and I2 ORed with I3 and I4. So this is this circuit over here. Now what I want to do is, so let me do this. This is I1, I2, I3, I4. This is this circuit right on top, and I want to build a multiplexer out of that. How do I build a multiplexer? Well, this becomes the A input, and then I have an S input that gets complemented, connects to I2, and the S input connects to I3, and the B input connects to I4. Together, the white stuff and this yellow stuff, this inverter over here, build my multiplexer, and therefore this is the multiplexer with output W. Okay, what did I do which is different than before? Well, before I described the multiplexer using something, using its assign statement, using a always a statement, using something like that. But now what I'm doing is I'm describing this multiplexer in terms of some existing modules that I have already perhaps developed, and this is called module instantiation. So that's still another way of describing hardware. All of these I'm applying to a multiplexer, but then by this I'm just showing various ways things can happen. Like this is the always statement, that's the most behavioral, and this says that wait for an event on A, B, or S, and then the flow begins. But here we are more looking at the structure rather than the behavior. And so this is the circuit, and